In this lesson, we're going to look at radicals again. We'll review some of the skills that we've done before, and then we will add a few new skills. And you'll see how radicals or roots are related to exponents. So a couple of things to remember, that a positive number can have two square roots. So for instance, 36 has a square root of 6, but it also has a square root of -6 because -6 times -6 gives us 36. The principal square root is the positive root. So we often will just think of the positive root, and it's called the principal square root. And the radical symbol always denotes the positive square root. So here's the definition. If a and b are non-negative, if b squared equals a, then b equals the square root of a. And notice that we're just talking about this positive root here. If you want to think of the negative or consider the negative square root, which we do sometimes, we use a negative sign in front of the radical sign to designate the negative square root. So if we think about 49, it has two square roots, 7 and -7. 7 is the principal square root, and if we say that if we use this symbol to talk about the square root of 49, we're really only talking about positive 7. So if we want to talk about the negative root as well, we stick a negative sign in front of the radical. The negative root of 49 is -7. So let's look at a couple of examples here. And again, it's very helpful when you see these examples to press pause, try them, and then check your answers. So the square root of 25 is 5 because we're only considering the positive root. Here, because of the negative, we're considering the negative root, so it's -6. The square root of 1/16, there are a couple of ways to do that, but so you could take this, you could separate it into this so that you've got so you've got the square root of 1 over the square root of 16, giving you 1/4. But if your mental math skills are really strong, you might recall 1/4 times 1/4 would be 1/16. So you could go straight to the 1/4. The radical symbol extends longer if it's covering longer. So it then becomes like a grouping symbol, almost like parentheses. So you need to do what's inside or under the radical sign first. So we have to add the 9 and the 16 first. So that'll give us 25 and giving us then the square root of 25, which is 5. And E is different because it's two separate radicals. So we do the square roots first. So we'll do the square root of 9, which is 3, plus the square root of 16, which is 4, which gives us 7. Okay, so it's important to see that distinction between those two. So when we're solving an equation that has square roots in it, or if we're simplifying, and we're going to do a few simplifying things as well, it's important to recognize that for instance, in A here, there are two possible values for x. There are two different numbers that if I square them will give me 121. So if I look at this equation, I'm going to get 1x, I'm going to take the square root of both sides so that x equals the square root of 121, but I have to consider the negative root as well. So I can say x is the square root of 21 or x equals the negative root of 121, which would give us x equals 11 or x equals -11. There's a nice shortcut for writing that, and you could write x equals plus or minus 11. And that shows there's two values for x, one positive and one negative. And that's entirely correct to do that. And again, if your mental math skills are strong, you can do that in one step. You don't need to show a middle step here. In question B, I need to do a little bit of rearranging. Before you take the square root of both sides, get the x squared term by itself. So in this case, I'm going to divide both sides by 7 so that I have x squared equals 5. And since 5 does not have a nice square root, I'm going to solve this just by saying x is equal to the positive or negative square root of 5. And that's my exact answer for that question. If you were doing a word problem asking you how long a particular thing is or something like that, you might then be asked to use a calculator and round that to a specific number of decimals. But this, leaving it in its radical form, simplified radical form, is actually gives you the exact answer. So let's take a look at a couple of these. Simplifying these radicals. If I have the square root of x squared, that just gives me x, okay? Because x times x gives me x squared. So by definition, okay? When I've got x to the power of 4, I'm taking the square root of that. So I want to know what multiplies by itself to give me x to the power of 4. And that would be x squared, okay? Since x squared times x squared equals x to the power of 4. If you think to the exponent rules where we add those together. So if I had another one where it was the square root of x to the power of 6 is going to be x cubed, because x cubed times x cubed will give me 6. So when you have an even exponent and you're taking the square root of it, you can just cut it in half. Okay, and that will give you your simplified version. Now let's take a look at x to the power of 5. It's not an even exponent, so I can't just cut it in half, but I can simplify it. If you think of how we simplified radicals before, we looked for perfect squares that would go into the radical. So if I think of perfect squares that go in there, well, x squared is a perfect square, and so is x to the power of 4. So we could write this as the square root of x to the power of 4 times the square root of x. We're using the same rules of multiplication and division for radicals with x's in them as we were doing for numbers. We could separate them out or we could put them together. So this still multiplies. So if I add the exponents on these, I'll still get x to the power of 5. Okay? Now with the square root of x to the power of 4, though, is x squared. So x squared root x is the simplified version of x to the power of 5. Let me just clarify that. That's a multiplication symbol, not a subtraction symbol. All right, let's take a look at a few more where we're simplifying. Some of these look like ones we've done before, and then some of them have the x's in them, so they look a little bit more abstract. So we have looked at ones like the square root of 700 before, and we looked for perfect squares that were factors of 700. And so in this case, it would be 100 times 7 gives us 700, and the square root of 100 is 10, so that's 10 root 7. So we've done questions like that before. We've done questions like B before, but without the x's. And the first thing we did was actually multiply and combine these and then looked for perfect squares. So this will be when I multiply 12x by 4x, I actually will then get 48x squared. And now I look for perfect squares that go into 48 and into x squared. So 48 is 16 times 3, so that's root 16 times root 3 times root x squared. Now there's a couple of things here that are perfect squares, the 16 and the x squared. So we do the perfect square numbers first are written, so that gives me 4. Then we take the letters or the variables, so the square root of x squared is x, and then we leave our radical. Okay, and if there was still an x or something else under that radical, it would just stay under the radical. But again, always the numerical coefficients first, and then the variables, then the radicals. And the radicals will also go numerical coefficients first, and then radicals. Question C, you've seen a couple of questions like that quite recently. In fact, one was on your last test like this. And we can do that two ways again. We can separate that out as the square root of 81 over the square root of 16, which gives us 9/4. And because 16 doesn't go evenly into 81. If it was 16, if it was 80 over 16, you would simplify that number first, do that divide, simplify it, and then try to simplify the radical. Question D is a division question as well. And let's do the dividing because 4 is a perfect square, but there's probably more in that 128 that are also perfect squares, and we can simplify these x's as well. So this is equal to 128 divided by 4 will be 32. X cubed divided by x will give me an x squared. So this is now just the square root of 32x squared. Perfect squares that go into 32 would be 16 times 2 is 32, and then we still have an x squared here. So that will give us 4x root 2. So the square root of 16, the square root of x squared, and then root 2. And that's your simplified version of that question. Okay, we've done square roots, lots of that. We've added a little bit of extra skill. We're now going to look at other roots. So what happens when it's not just a square root, okay? So if we have the nth root of a, which is how you would say that, the nth root of a equals b, means that b to the power of n equals a. So if n is even, a is non-negative, and b is also non-negative. If n is odd, then a and b can be any real number. So n, in this case, when you see a number in the radical sign, it's called the index of the radical. Okay, and if you're taking the square root of a number, so I just want to explain this even and odd thing. If I do the square root of negative 36, there's no real answer. Okay, there's no real square root of a negative number. Okay, but there might be for a cubed root. So for instance, the cubed root of 8, of negative 8, is negative 2, because negative 2 to the power of 3 gives you negative 8. Okay, so when you've got a negative under the radical and an odd index, you can have negatives. If you have an even index, you'll never have a real answer. So let's do a couple of different roots just so that you can see to be comfortable with them. And you will see the ones, the cubed fourth and fifth roots that you need to know. You will see those in your textbook on page 52. So the cubed root of 64 is 4, since 4 cubed is equal to 64. The fourth root of 81 is 3, since 3 to the power of 4 equals 81. And the fifth root of negative 32 is negative 2, because if I did negative 2 to the power of 5, I would have negative 32. Okay, so to do the simplifying, you really need to master the perfect squares, cubes, fourths, and fifths, at least to a certain level. So those will be required in order to do these smoothly. So let's take a look at them one at a time. We've got the cubed root of 24, so I want to know the perfect cube. So 1 cubed is 1, so we just ignore it. But 2 cubed is 8, 3 cubed is 27, etc. So 8 goes into 24, so we can split this into the cubed root of 8 times the cubed root of 3, because 8 times 3 is 24, and the cubed root of 8 is 2. So this gives me 2 cubed root of 3. Be careful not to forget to write the index in these, okay? And it makes it a little bit awkward. It's hard to do that neatly, but do your best to be clear with including the index with the radical. Question B, I'm going to multiply first. So I'm going to get the fourth root of 32, and then I'm going to look for perfect fourth powers that go into 32, and 16 goes into 32, so that's the fourth root of 16 times the fourth root of 2. The fourth root of 16 is 2, so that gives me 2 times the fourth root of 2. Question C, we're looking at the cubed root of a fraction again, or you could turn it into a division. You could think of that as the cubed root of 125 over the cubed root of 27. Pretty soon these numbers are going to be very familiar to you because there's not a huge amount of perfect cubes that you're expected to know. The cubed root of 125 is 5. The cubed root of 27 is 3. So 5/3 is the answer. Okay, adding, subtracting, combining cubed roots. Same rules as for square roots. We can only combine them if the radical is the same, and the index and the number under the radical need to be the same. So the index and the radicand must be equal. Okay, so these are both cubed roots, so we want to see if we can simplify that cubed root of 16 so that we can combine those. So if you think about perfect cubes that go into 16, 8 is one of them. So this is equal to 5 times the cubed root of 8 times the cubed root of 2 minus 11 times the cubed root of 2. So the cubed root of 8 is 2, so that becomes 5 times 2 times the cubed root of 2 minus 11 times the cubed root of 2. So that gives us 10 cubed root of 2 minus 11 cubed root of 2, which will give us negative 1 times the cubed root of 2. So we could just write that as negative cubed root of 2. Okay, so same rules and perhaps a cue card with the perfect cubes, fourth powers, and fifths that you need to know. Rationalizing the denominators. We're going to look at that again as well because it gets very interesting. So 10 over the square root of 2. Remember to rationalize the denominator, or to have a radical in simplified form, we can't have a radical in the denominator. So we learned to multiply by the number 1, but multiply numerator and denominator by whatever root will give us a perfect square in the denominator. So our numerator now is 10 root 2. Our denominator is 2. And we can do some simplifying. 2 goes into 10 5 times, so that gives us 5 root 2. What about this second one? B here. If I multiply top and bottom by the square root of 3, oops, let me just write that differently here. If I multiply by the square root of 3 in the numerator and the denominator, the numerator will be 7 root 3. That's fine. But really, I have to distribute that square root of 3 to both terms. So the square root of 3 times the square root of 3 will give me 3, but I'll still end up with a square root in the denominator because I'll have 5 root 3. So that does not work. Okay? And in order to make that work, we have to learn a new term, which is called a conjugate. And I've got a link here. Let's see if it's going to work. Okay, it's not going to work. But on your notes, it should work for you to be able to open the definition of conjugate. And a conjugate is when you have a binomial, so two things that are added or subtracted, you change the operation in between. So if I have 3 plus x, its conjugate will be 3 minus x, okay? And vice versa. Whenever we multiply conjugates, magic happens. Well, it's not really magic, but it works something very special happens. So we've got, let's try these. Let's do the a plus b times the a minus b first. Keep in mind when you're multiplying, we're using the distributive property. I need to multiply this a in the first parentheses by both terms in the second. So I'll have a squared minus ab. And then I need to multiply the b by both terms in the second. So that will give me plus BA, but I'm going to write them in alphabetical order, AB, and B times negative B will be negative B squared. Notice that in the middle I have a negative AB and a positive AB. Those add up to 0, so I end up with A squared minus B squared. Okay, if I take 2 plus root 7 times 2 minus root 7, I'm going to follow those same steps. Multiply both terms by 2 and then multiply both terms by root 7. So I end up with 2 squared, or 4, and minus 2 root 7. And then when I multiply this root 7 by both terms, I end up with a plus 2 root 7 and then a negative root 7 squared. So these two middle terms add up to 0 again because I've got a negative 2 root 7 and a positive 2 root 7. So I end up with 2 squared minus root 7 squared. And now let's evaluate what that is. That gives me 4 minus 7. Square root of 7 times the square root of 7 gives me 7, which is negative 3. The beauty of multiplying by a conjugate is that the same pattern happens every time so that you don't actually even have to do all those middle steps. You're squaring the first term and then you're squaring the second term. So if I look at this example on the left with a 2 plus root 7, I end up with 2 squared minus root 7 squared, which gives me then the 4 minus 7, which is the negative 3. Here I end up with a squared minus b squared. Okay, so multiplying by a conjugate is a beautiful thing, and you'll see it again when we work with polynomials. But what it does is it helps us to rationalize the denominator because we end up getting rid of the radicals. So we multiply top and bottom by the same thing, but we choose the conjugate of the denominator. So it'll be 5 minus root 3 to give the conjugate, and then 5 minus root 3. So keep in mind that we're not changing the value of this radical because we're multiplying it by 1. 5 minus root 3 over 5 minus root 3 is 1, okay? But I'm choosing a very special value for 1 that, that allows me to rationalize that denominator, okay? Let me just flip to the right page here. All right, so my numerator now will become 7 times 5 minus root 3. My denominator will become 5 squared minus root 3 squared. 5 squared minus root 3 squared. Okay, I want you to get used to the term of thinking in terms of a squared minus b squared. So square the first term, square the second term. So the numerator, 7 times 5 minus root 3. We'll leave it at that for now. And 5 squared is 25. Root 3 squared is 3. So we have 25 minus 3. So that gives us 7 times 5 minus root 3 all over 22. Now, as far as simplifying goes, if the 7 and the 22 had something in common, a factor in common, you would be able to simplify at this stage. They don't, so we can't simplify. You could also choose to multiply through the brackets here and write that as 35 minus 7 root 3 all over 22. Both of those are equally correct and equally nice as far as form goes. So let's take a look at question C. I've got root 3 over 5 minus root 2. So again, think about what's the conjugate of the denominator. 5 minus root 2 becomes then 5 plus root 2. And we'll multiply top and bottom by the same thing. So now in my numerator, I've got root 3 times 5 plus root 2. And in my denominator, oops, I've got a squared, so it'll be 25 minus b squared, so minus root 2 squared. Okay, a squared minus b squared. Let's multiply through in the numerator because that's not nice to have the radical out front and whole numbers inside the brackets. So that will become 5 root 3 plus root 6 all over, and that'll be root 2 squared gives me 2, so 25 minus 2 over 23. And we're finished. And that's the end of this lesson, which I know is a pretty long one. So hang in there. This is some fun stuff to work on.